Imagine a star moving so fast through space that it could travel from Earth to the Moon in just 6 minutes. Not a spacecraft, not a meteor, but an entire star, a massive ball of nuclear fire containing more matter than 1 million Earths, hurtling through the galaxy at speeds that seem to defy the very nature of how we think celestial objects should behave. This isn't science fiction, this is real, and it's happening right now in our own Milky Way galaxy. The star we're talking about is called S5HVS1, and it's moving at an absolutely staggering speed of 1,017 miles per second. To put that in perspective, that's nearly 4 million miles per hour, fast enough to circle the entire Earth in just under 4 minutes. But here's what makes this even more mind-bending. This star isn't just drifting through space at this incredible velocity, it's actively escaping our galaxy entirely, never to return. How is this possible? What cosmic force could possibly accelerate a star, an object so massive it would take light itself 4.5 years to reach us from the nearest one, to such incomprehensible speeds? And perhaps more intriguingly, what does the existence of these stellar speed demons tell us about the hidden violence and power lurking in the seemingly peaceful depths of space? The story of hypervelocity stars, as astronomers call them, begins with a mystery that challenged everything we thought we knew about how stars move through galaxies. For most of human history, we've looked up at the night sky and seen what appears to be a stable, unchanging tapestry of lights. The ancient Greeks called them fixed stars, precisely because they seemed to maintain their positions relative to each other across human lifetimes. Even as our understanding of the universe evolved, we continued to think of stars as relatively sedate objects, following predictable orbital paths around the galactic center like planets around the sun. But the universe, as we've learned time and again, refuses to conform to our expectations of cosmic tranquility. The first hints that something extraordinary might be happening came in the late 20th century, when astronomers began to develop more sophisticated ways of measuring stellar velocities. Using the Doppler effect, the same principle that makes an ambulance siren change pitch as it passes by, they could detect how fast stars were moving toward or away from us by analyzing the subtle shifts in the color of their light. What they found was puzzling. Most stars in our galaxy's disk move at relatively modest speeds, typically between 20 to 40 miles per second relative to the galactic center. This made sense given our understanding of galactic dynamics and the gravitational forces at play. But occasionally, astronomers would encounter a star that seemed to be moving far too fast for comfort. These weren't just slightly speedy stars, they were objects moving at hundreds of miles per second, speeds that seemed impossible to explain through normal stellar evolution or galactic dynamics. The real breakthrough came in 2005, when a team of astronomers led by Warren Brown at the Harvard-Smithsonian Center for Astrophysics made a discovery that would revolutionize our understanding of stellar dynamics. They had been conducting a systematic survey of stars in the outer regions of our galaxy when they stumbled upon something truly extraordinary. A star designated as SDSJ 090745.0 plus 024507 that was moving at an unprecedented 853 miles per second, nearly 2 million miles per hour. This wasn't just fast, it was impossibly fast by any conventional understanding of stellar physics. The star was moving so quickly that it was clearly in the process of escaping the Milky Way's gravitational pull entirely. Within 100 million years, it would be sailing through the void between galaxies, a cosmic exile traveling through the darkness of intergalactic space. But how does a star achieve such tremendous velocity? The answer lies in one of the most violent and extreme environments in our galaxy, the immediate vicinity of the supermassive black hole that lurks at the Milky Way's center. This black hole, known as Sagittarius A star or SGR A star, contains approximately 4 million times the mass of our Sun compressed into a region smaller than the orbit of Mercury. The gravitational forces near this monster are so intense that they can accelerate objects to significant fractions of the speed of light. The mechanism responsible for creating hypervelocity stars is elegantly violent in its simplicity. It begins with what astronomers call a binary star system. two stars locked in a gravitational dance orbiting around their common center of mass. These stellar partnerships are incredibly common throughout the galaxy. In fact, most stars exist as part of binary or multiple star systems rather than as solitary objects like our Sun. Now, imagine one of these binary pairs wandering too close to the galactic center, drawn in by the immense gravitational pull of the central black hole. As the binary system approaches Sagittarius, a star, the extreme tidal forces begin to tear the partnership apart. The gravitational field of the black hole is so strong and changes so rapidly with distance that it affects each star in the binary pair differently. One star finds itself pulled more strongly toward the black hole, while its companion experiences a slightly weaker gravitational tug. This difference in gravitational force, what physicists call a tidal force, acts like a cosmic crowbar prying the two stars apart. But here's where the physics becomes truly spectacular. As one star spirals inward toward the black hole, destined for eventual consumption, its former partner receives what amounts to a gravitational slingshot effect. The energy that once bound the binary system together is suddenly released, launching the surviving star away from the galactic center at tremendous velocity. It's remarkably similar to what happens when you're spinning a weight on a string and the string suddenly breaks. The weight flies off in a straight line, carrying with it all the energy that was stored in its circular motion. In the case of hypervelocity stars, that string-breaking moment occurs when the black hole's gravity tears apart the binary system and the escaping star carries away the orbital energy of what was once a gravitationally bound pair. This process, known as the Hills mechanism, after astronomer Jack Hills, who first proposed it in 1988, can accelerate stars to velocities of 1,000 miles per hour per second or more, speed sufficient to escape the gravitational pull of our entire galaxy. The mechanism is so efficient that astronomers estimate it should produce roughly one hypervelocity star every 100,000 years or so, meaning there could be thousands of these stellar speed demons currently racing through our galaxy. But S5HVS1, the record holder we mentioned at the beginning, represents something even more extreme. Discovered in 2019 by a team led by Sergei Kapozov at Carnegie Mellon University, this star isn't just moving fast, it's moving faster than should be theoretically possible through the Hills mechanism alone. At over 1,017 miles per second, S5HVS1 pushes the boundaries of what we think the galactic center can achieve through binary disruption. This has led astronomers to consider even more exotic possibilities. Perhaps S5HVS1 wasn't launched by a simple binary disruption, but by something far more violent. The encounter between a binary star system and not one, but two supermassive black holes. There's growing evidence that our galaxy's center may have experienced a merger with another galaxy in the distant past, temporarily bringing together two supermassive black holes in a cosmic dance of unimaginable violence. During such an encounter, the gravitational dynamics become far more complex and chaotic. The interaction between multiple supermassive black holes and nearby stellar systems could potentially accelerate stars to even higher velocities than the standard Hills mechanism would predict. It's like the difference between being hit by a baseball and being caught in the explosion of a hand grenade. Both will send you flying, but one packs considerably more punch. To truly appreciate the significance of hypervelocity stars, we need to consider what their existence tells us about the nature of our galaxy itself. For decades, astronomers viewed the Milky Way as a relatively stable, well-behaved spiral galaxy, slowly rotating in space like a cosmic pinwheel. The discovery of hypervelocity stars has revealed that our galactic home has a much more violent and dynamic history than we previously suspected. These stellar exiles serve as archaeological evidence of past catastrophes, cosmic fossil records of moments when the normally stable architecture of our galaxy was violently disrupted. Each hypervelocity star represents a snapshot frozen in time, carrying information about the conditions that existed at the galactic center when it was launched on its journey toward intergalactic space. By studying the trajectories of these runaway stars, astronomers can work backward to determine not only when they were ejected, but also what the environment around our galaxy's central black hole was like at various points in the past. Some hypervelocity stars appear to have been launched relatively recently, within the last few million years, while others may have been racing through space for hundreds of millions of years, carrying with them secrets about our galaxy's ancient history. The implications extend far beyond simple curiosity about stellar dynamics. Hypervelocity stars provide crucial insights into the behavior of supermassive black holes, objects so extreme that they exist at the very limits of our understanding of physics. By observing how these black holes interact with nearby stellar systems, we gain valuable clues about the nature of gravity itself under the most extreme conditions imaginable. Moreover, the study of hypervelocity stars has opened up entirely new avenues of research into galactic evolution and dynamics. These cosmic speedsters serve as tracers, helping astronomers map out the gravitational structure of our galaxy and understand how it has changed over billions of years of cosmic history. They're like breadcrumbs scattered through space, marking the path of our galaxy's tumultuous past. The technology required to detect and study hypervelocity stars represents a triumph of modern astronomical instrumentation. The European Space Agency's Gaia mission, launched in 2013, has been particularly crucial in this effort. Gaia is essentially a cosmic surveyor, precisely measuring the positions and motions of over 1 billion stars in our galaxy with unprecedented accuracy. What makes Gaia so revolutionary is its ability to detect proper motion, the subtle movement of stars across the sky over time. While the Doppler effect can tell us how fast a star is moving toward or away from us, it can't reveal motion perpendicular to our line of sight. Gaia fills in this missing piece of the puzzle, providing a complete three-dimensional picture of stellar motion that allows astronomers to identify hypervelocity stars with confidence. The precision required for this work is almost incomprehensible. Gaia can measure stellar positions to an accuracy equivalent to determining the width of a human hair seen from a distance of 600 miles. This extraordinary precision is necessary because even the fastest hypervelocity stars appear to move incredibly slowly across the sky from our perspective on Earth. It's like trying to measure the progress of a snail by watching it for just a few seconds. You need incredibly sensitive instruments to detect any motion at all. The discovery process itself is a testament to the power of modern data analysis techniques. The Gaia mission generates enormous quantities of data, measuring the positions and properties of stars at a rate that would have been unimaginable just a few decades ago. Identifying hypervelocity stars within this vast dataset requires sophisticated computer algorithms that can sift through millions of stellar measurements to find the handful of objects with unusual motion patterns. This process has revealed that hypervelocity stars are not as rare as once thought. What began with the discovery of a single exceptional object in 2005 has now grown into a catalog of dozens of confirmed hypervelocity stars, with many more candidates awaiting further study. Each new discovery adds another piece to the puzzle of our galaxy's violent history and the extreme physics operating at its center. But the story of hypervelocity stars becomes even more intriguing when we consider their ultimate fate. These stellar refugees are not simply fast-moving stars within our galaxy. They are genuine escapees, destined to spend the rest of their lives wandering through the vast emptiness of intergalactic space. Once they break free from the Milky Way's gravitational embrace, there is no force in the universe capable of turning them around and bringing them home. The journey of a hypervelocity star into intergalactic exile is a cosmic odyssey of almost unimaginable loneliness. Our galaxy is approximately 100,000 light-years across, so even at their tremendous speeds, it takes these stars millions of years to traverse the full width of the Milky Way and escape into the void beyond. During this journey, they gradually leave behind everything familiar: the dense stellar neighborhoods of the galactic disk, the scattered star clusters of the halo, and eventually even the faint glow of distant galaxies. Once in intergalactic space, a hypervelocity star becomes truly isolated. The nearest neighboring galaxy, Andromeda, lies over 2 million light-years away. Even at a speed of 1,000 miles per second, it would take a hypervelocity star roughly 3 billion years to cover that distance, longer than complex life has existed on Earth. For all practical purposes, these stars are condemned to an eternity of solitude, burning their nuclear fuel in the darkness between galaxies with no possibility of interaction with other stellar systems. This cosmic exile raises profound questions about the nature of stellar evolution in extreme environments. We understand how stars live and die within galaxies, where they're surrounded by gas clouds that can potentially form new stellar generations, and where their death throes can influence the formation of future stars. But what happens to a star that spends its entire life in the sterile environment of intergalactic space? The answer is both melancholy and fascinating. A hypervelocity star in intergalactic exile will continue to burn its nuclear fuel much as it would within a galaxy, fusing hydrogen into helium in its core and shining with the same brilliance. But when it eventually exhausts its fuel and reaches the end of its life, there will be no cosmic recycling program to give its atoms a second chance at stellar formation. The heavy elements forged in the star's core, carbon, oxygen, silicon, iron, will be scattered into the intergalactic void, forever lost to the process of star formation. In a sense, hypervelocity stars represent a form of cosmic brain drain, carrying away from our galaxy the precious heavy elements that are essential for the formation of planets and potentially life itself. Each escaping star takes with it atoms that were painstakingly created through billions of years of stellar nucleosynthesis, removing them permanently from the galactic ecosystem that gave them birth. The philosophical implications of hypervelocity stars extend far beyond their role as cosmic curiosities. These stellar exiles force us to confront fundamental questions about belonging, isolation, and the nature of home on cosmic scales. In human terms, we might think of them as immigrants who can never return to their homeland, carrying with them only the memories encoded in their stellar composition of the violent events that launched them into exile. But perhaps there's also something deeply hopeful about hypervelocity stars. They represent the ultimate expression of freedom in a universe where most matter is bound by gravitational forces into predictable cyclic patterns. While planets orbit stars, stars orbit galactic centers, and galaxies orbit within galaxy clusters, hypervelocity stars have broken free from all these gravitational chains. They are the universe's nomads, wandering freely through space according to no master's will. From a more practical perspective, the study of hypervelocity stars has important implications for our understanding of the Milky Way's future evolution. As these stars carry mass and energy away from our galaxy, they contribute to a gradual process of galactic erosion that occurs over hundreds of billions of years. While the effect is minimal on human timescales, over cosmic time periods, the cumulative loss of hypervelocity stars represents a significant drain on our galaxy's stellar population. This process becomes particularly relevant when we consider the eventual collision between the Milky Way and the Andromeda Galaxy, predicted to occur in approximately 4.5 billion years. The gravitational chaos of this galactic merger will likely create conditions similar to those that produce hypervelocity stars today, but on a much larger scale. The interaction between two supermassive black holes and their surrounding stellar populations could launch millions of stars into intergalactic space, fundamentally altering the structure and evolution of the resulting merged galaxy. Recent computer simulations of this future galactic collision suggest that hypervelocity star production will increase dramatically during the merger process. The combined gravitational influence of two supermassive black holes, along with the general disruption of stellar orbits throughout both galaxies, will create ideal conditions for accelerating stars to escape velocities. Some models predict that as much as 10% of the stars in both galaxies could be ejected during the merger, creating a vast diaspora of stellar exiles wandering through intergalactic space. The detection and study of hypervelocity stars has also opened up new possibilities for testing our understanding of fundamental physics. These extreme stellar velocities provide natural laboratories for studying the behavior of matter and energy under conditions that cannot be replicated on Earth or in conventional astronomical observations. The gravitational fields responsible for accelerating stars to such tremendous speeds approach the limits where Einstein's theory of general relativity begins to show significant deviations from Newton's simpler gravitational laws. By carefully measuring the trajectories and properties of hypervelocity stars, astronomers can potentially detect subtle effects predicted by general relativity that would be impossible to observe through other means. These stars serve as test particles moving through some of the most extreme gravitational environments in the universe, carrying with them information about the nature of spacetime itself in the vicinity of supermassive black holes. The study of hypervelocity stars has also contributed to our understanding of dark matter, the mysterious invisible substance that appears to make up roughly 85% of all matter in the universe. The trajectories of these high-speed stars depend not only on the visible matter in our galaxy, but also on the distribution of dark matter throughout the galactic halo. By tracking hypervelocity stars as they move through different regions of the galaxy, astronomers can map out the three-dimensional structure of dark matter in ways that complement other detection methods. This dark matter mapping capability has revealed that our galaxy's invisible halo is far more complex and dynamic than previously suspected. Rather than forming a simple symmetric sphere around the visible galaxy, dark matter appears to be distributed in a lumpy, irregular pattern that reflects the violent merger history of the Milky Way. Hypervelocity stars serve as sensitive probes of this dark matter distribution, their paths deflected by gravitational influences from invisible mass concentrations. As our observational capabilities continue to improve, astronomers expect to discover hypervelocity stars with even more extreme properties. The upcoming Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have the capability to survey vast regions of sky with unprecedented sensitivity, potentially revealing hypervelocity stars that are too faint or distant to detect with current instruments. There's also growing interest in searching for hypervelocity stars that originated not from our own galaxy, but from external galaxies. If the mechanism that produces hypervelocity stars operates in other galaxies as well, and there's every reason to believe it should, then intergalactic space may be populated by a sparse but widespread population of stellar wanderers from many different galactic systems. Detecting such intergalactic hypervelocity stars would provide unique insights into the properties of other galaxies and their central black holes. The possibility of intergalactic hypervelocity stars raises tantalizing questions about the connectivity of the universe on the largest scales. Could stars ejected from one galaxy eventually be captured by another, serving as a form of cosmic genetic exchange between distant galactic systems? While the probability of such capture events is extremely small, the universe is vast and old, suggesting that even rare occurrences may have happened many times over cosmic history. Some astronomers have speculated about even more exotic possibilities. If hypervelocity stars can carry heavy elements from one galaxy to another, they might also serve as vectors for the spread of complex chemistry throughout the universe. The carbon, oxygen, and other elements essential for life that are manufactured in stellar cores and dispersed when stars die could potentially be transported across intergalactic distances by hypervelocity stars, seeding distant regions with the raw materials necessary for planet formation and biological evolution. This concept of stellar-mediated panspermia, the idea that life's building blocks could be transported between galaxies by hypervelocity stars, remains highly speculative, but it illustrates the far-reaching implications of these cosmic speed demons. They represent not just isolated curiosities, but potentially important agents in the large-scale evolution and chemical enrichment of the universe. The human perspective on hypervelocity stars inevitably returns us to questions of scale and significance. In our everyday experience, a journey of a few hundred miles represents a significant undertaking requiring hours of travel and careful planning. For a hypervelocity star, a distance equivalent to traveling from Earth to the Moon represents less than 10 minutes of flight time. The scales involved are so vast that they challenge our ability to develop any intuitive understanding of these phenomena. Yet perhaps this is precisely why hypervelocity stars are so important to our broader understanding of the universe. They force us to confront the inadequacy of human-scale thinking when dealing with cosmic phenomena. They remind us that the universe operates according to principles and scales that are fundamentally alien to our everyday experience, yet still comprehensible through the application of scientific reasoning and mathematical analysis. The story of hypervelocity stars is ultimately a story about the power of gravity itself. Gravity as a creative and destructive force capable of accelerating entire stars to velocities that seem impossible. Gravity as the sculptor of galactic architecture and the architect of cosmic violence. These stellar speed demons represent gravity's ultimate expression of power, the final demonstration of what happens when the universe's fundamental forces operate without restraint in the most extreme environments imaginable. But the story is also about the resilience and persistence of scientific inquiry. The discovery of hypervelocity stars required decades of technological development, from the initial recognition that some stars seem to be moving unusually fast, to the deployment of space-based telescopes capable of measuring stellar motions with unprecedented precision. Each new discovery has built upon previous work, gradually revealing a picture of our galaxy that is far more dynamic and violent than anyone suspected just a few decades ago. As we look toward the future, the study of hypervelocity stars promises to continue yielding new insights into the nature of our cosmic environment. Advanced gravitational wave detectors may eventually be sensitive enough to detect the space-time ripples produced when binary star systems are disrupted by supermassive black holes, providing a new window into the physics of hypervelocity star formation. Deep space telescopes may reveal the faint traces of hypervelocity stars in distant galaxies, allowing us to study these phenomena on cosmic scales. The ultimate significance of hypervelocity stars may lie not in their individual properties, but in what they reveal about the interconnected nature of cosmic evolution. They demonstrate that even the most extreme and violent events in the universe, the disruption of stellar systems by supermassive black holes, are connected to larger patterns of galactic evolution and cosmic structure formation. They show us that our galaxy is not a static, unchanging system, but a dynamic environment shaped by billions of years of violent encounters and gravitational catastrophes. In contemplating these stellar exiles racing through space at millions of miles per hour, we're confronted with one of the universe's most profound paradoxes. Here are objects of immense mass and energy, burning with the fire of nuclear fusion, yet destined for ultimate isolation in the cold darkness of intergalactic space. They represent both the universe's capacity for violence and its indifference to the fate of individual stars, galaxies, and planetary systems. Perhaps that's the most important lesson hypervelocity stars have to teach us. In a universe capable of accelerating entire stars to escape velocity, the forces that govern our own small corner of space, the gravitational dance of planets around the sun, the gradual evolution of stellar populations, the slow chemical enrichment of galactic regions, represent islands of relative stability in an ocean of cosmic chaos. Yet, these islands of stability are not permanent. They exist at the mercy of larger forces that operate on scales we can barely comprehend, forces capable of disrupting entire stellar systems and scattering their components across millions of light-years of space. The hypervelocity stars racing through our galaxy today serve as reminders that even the most stable-seeming cosmic structures are temporary, subject to disruption by events of unimaginable violence and power. But rather than finding this prospect terrifying, perhaps we should find it awe-inspiring. We live in a universe so rich in energy and so vast in scale that it can casually accelerate objects containing the mass of millions of Earths to velocities approaching the speed of light. We inhabit a cosmic environment so complex and dynamic that single events at galactic centers can influence the evolution of stellar systems for billions of years into the future. The fastest stars in our galaxy are more than just curiosities for astronomers to study. They are messengers from the most extreme environments in the universe, carrying information about forces and phenomena that operate at the very limits of physical possibility. They are proof that the universe we inhabit is far stranger, more violent, and more wonderful than any human imagination could have conceived. As we continue to discover and study these cosmic speed demons, we're not just learning about stellar dynamics or galactic evolution. We're confronting fundamental questions about the nature of reality itself, about the forces that shape the largest structures in the universe, and about our own place within the vast, violent, and ultimately magnificent cosmic environment that we call home. In the end, perhaps the most remarkable thing about hypervelocity stars is not their tremendous speed or their exotic origin stories, but simply the fact that we can detect and study them at all. In a universe spanning hundreds of billions of light years and containing trillions of galaxies, the fact that we can identify individual stars racing through space at millions of miles per hour represents one of the greatest triumphs of human scientific achievement. These stellar speed demons, racing toward their lonely exile in intergalactic space, carry with them not just the heavy elements forged in stellar cores, but also the hopes and curiosity of an entire species that has learned to read the stories written in starlight. They remind us that no matter how vast and violent the universe may be, it remains comprehensible to creatures willing to look up at the night sky and ask the simple question, what's out there and how does it work? The answer, as hypervelocity stars demonstrate, is more remarkable than we ever dared imagine.